When looking at Fischer projections, the first thing you want to do is try to recognize these are written out as flat images meant to represent three-dimensional molecules. So here I'm going to draw out D-glyceraldehyde, and we'll talk about what that is here in a second. That's going to have a CHO group on top. That's an aldehyde, as well as a hydroxyl group over here on the right, a CH2OH on the bottom, and a hydrogen over here on the left. By convention, D versus L is determined based on D-glyceraldehyde versus L-glyceraldehyde, in which the OH group is on the right in D-glyceraldehyde, and the OH group is on the left in L-glyceraldehyde. That's really kind of all you need to know for the MCAT. If we were looking at amino acids, D versus L amino acids instead, obviously there's no OH group on an amino acid chiral carbon, on the alpha carbon in the center of the amino acid. And so we want to put the NH3 on the right because in that case, it would be the highest priority group. So D versus L just means for D that the highest priority group is on the right, and for L that the highest priority group is on the left. But what do right and left mean here anyway? So in Fischer projections, you want to think about all horizontal lines as being pressed up out of the page. So those would be kind of like the wedges in your wedge and dash conformation. So here I'm just writing horizontal lines, horizontal equals out of page. And for the vertical lines, you want to think about them as being down, projected down into the page. All right, so this is kind of like the dashes in that wedge dash conformation that many of you have seen before. We'll talk about that in just a second as well. Vertical equals into page. And so you can redraw the Fischer projection as looking something like this, where again, we've got our vertical lines going down into the page. So here we've got our CHO, and again, that's just an aldehyde because it's D-glyceraldehyde that we're looking at. And our other vertical line going down into the page as well, that's CH2OH. And then we have our horizontal lines coming up out of the page. Here we have our OH on the right because it's the high priority group, and we're looking at D-glyceraldehyde. I'm gonna go ahead and write that over here. So D-glyceraldehyde, just for anybody looking back at this or looking at the notes later. D-glyceraldehyde is the molecule that we're concerned with. And then our hydrogen over here coming up out of the page on the left. So if we want to try to transpose this onto that three-dimensional structure that you probably recognize and many of you probably use to determine R versus S, it's not actually that difficult to do it. If you can just imagine that we grab onto this H and OH, the two horizontal arms of this molecule right now, and just start to rotate that top group up to us, up out of, because currently it's projecting back into the page, but if we've rotated it up out into the plane of the page, so, pulling it, it was pressing down into the page, we're pulling it up into the plane of the page, then you could recognize that the bottom group is going to go back into the page further, and that the H and the OH, while they're still going to be sticking out of the page, are going to move down a little bit toward the plane as well. So what this is going to look like, I know that that's probably super confusing, but bear with me for a second. So as we rotate, we're basically grabbing this CHOH and rotating it upward toward ourselves. So rotating the whole molecule like that. What we're going to end up with is something that looks a lot like this. We're going to have a flat line here because, again, that's right there in the plane of the page. We brought it into the plane. And we're going to have our two groups that were sticking out of the page still sticking out, but now they've rotated down just a little bit to where they're a little bit less out of the page. So there's the H and the hydroxyl group. And then we're going to have our CH2OH that was perfectly back into the page, now still sticking back into the page, but it's moved up above the horizontal plane a little bit through this molecule. That's not that important, but just recognize now we've got two groups sticking out, one group back into the page and one group perfectly in the plane. And keep in mind, these are all 109.5 degrees apart from one another. Now that we've done that, I want to rotate just a little bit again. This time instead of rotating around the horizontal axis, we're going to rotate around the vertical axis. And we're going to rotate sort of this direction. And we're going to do it until this group here on the left, meaning the hydrogen in this case, ends up in the plane of the page as well. Once we do that, I'm going to move this thing over just a little bit. We'll move it over this direction. Once we do that, now we've got two functional groups that are inside the plane of the page in this molecule. And so we're stuck in this sort of thing, right? We've got our CHO and our hydrogen both in the plane of the page. And now we've got one group sticking out of the page. That would be the OH, right? Because we rotated it a little bit just to put that hydrogen in the plane, which means that OH is now sticking like perfectly out of the page at us. And then we still have the group that was in the very back, still in the very back here, CH2OH. And now we have something that we're a lot more familiar with, right? We've got the two in the plane, one out, one in the back. Whenever you look at this sort of a setup and attempt to determine R versus S, what you're supposed to do is assign priority each of these things based on the atomic number of the largest atom attached to the central carbon. And so here in that case, that's going to be the hydroxyl group, right? So we can assign it as priority number one. Priorities 2 and 3 are tied whenever we look at the atomic number of the atom attached to the central carbon. And so then we would just go to the next biggest atom that is attached to that atom. And in this case, we've got oxygen for both of them, which is also not helpful. However, the aldehyde here has 2 bonds to oxygen, whereas the hydroxyl group, or the alcohol in the back, only has 1 bond to oxygen. So for that reason, we're going to give this priority number 2. This gets priority number 3. And then hydrogen is always going to be, almost always going to be our lowest priority. Now we've numbered these things, we can see that if we are going to rotate around this molecule, we're going to go from the hydroxyl group over to the aldehyde group. And the direction that we need to go is based on the way that they are the closest, when we don't have to leap over something that's either into the page or out of the page. And what I mean here is that if we were going to go from this one over to the left, if we were to go around this hydrogen, for instance, we'd have to skip over something that's in the plane of the page in order to get to priority number 2. So we can't go that direction. We have to go this direction, because the one thing that we're skipping over is actually back behind the plane of the page. And so we don't need to really consider it as something that we're legitimately skipping over. So for this reason, we can see that we're rotating counterclockwise, right? And so you would call that S if the lowest priority group were in the back. However, since the lowest priority group is in the plane of the page currently, if it's in the plane of the page or in the front of the page, then you make a counterclockwise rotation BR. If it's in the back, then you make a counterclockwise rotation BS. So for this reason, we would call this molecule R. All right, and so that's the reason that we can determine that D-glyceraldehyde is the same as R-glyceraldehyde. And L-glyceraldehyde would be S-glyceraldehyde. We'll go through how to do that just by looking at the Fischer projection too, because I don't want you to have to convert this molecule all the way to this 3D conformation every single time you need to determine the stereo configuration around it. So for that reason, this one is R. Now, if we look at the Fischer projection for this exact same molecule, I'm going to redraw it down here a little bit lower. Again, we've got our functional groups that are going back into the page on the top and the bottom. And we have our functional groups sticking out of the page on the right and the left. So that by convention, if we want to determine the stereo configuration around the central carbon without converting it into that 3-dimensional molecule, I just wanted to show you what these look like from a 3-dimensional molecule perspective, but this way is actually a lot easier. So what I would recommend in this scenario is, again, rank all the priorities. So you've got priority 1, priority 2, priority 3, and priority 4. And again, this is just based on the atomic number of the biggest of the atom that's immediately attached to the chiral carbon, and then you move down to the next atom if there's a tie. So we've got priorities 1, 2, 3, 4 here. The next thing that you want to do is determine the direction that you need to rotate in order to go from priority 1 to priority 2. And in this case, in order to do that, we go from the OH over to the aldehyde. So we're moving this direction. Again, this is counterclockwise. You would think that counterclockwise, many of you have probably learned that counterclockwise typically means S, but that's not always the case. So counterclockwise means S if the low priority group, or lowest priority, is behind the plane of the page or projects down into the page. However, if the low priority group is not projecting down into the page, then counterclockwise means R, if lowest priority is out of page. In this case, whenever we're looking at the Fischer projection, we see that the low priority is on a horizontal arm, right? Which means that it's sticking up out of the page, which means that a counterclockwise rotation from priority 1 to priority 2 to priority 3 indicates the molecule is R. And so here we can see, again, we wrote D-glyceraldehyde because we knew that the highest priority was on the right side. And we know that that now is equal to R-glyceraldehyde, just like I said a second ago, because we rotated counterclockwise from high priority to number 2 to number 3, but the lowest priority group was sticking up out of the page because the horizontal arms are sticking out of the page in the case of the Fischer projection, whereas the vertical arms are sticking down into the page. There are some ways that you can very quickly interconvert one Fischer projection to another and determine whether they are the same molecule or whether they're different molecules. If you rotate three groups and hold one stationary, then you can know that that molecule is actually exactly the same molecule. So let's go ahead and do that really quick. I'm going to make up a molecule so that we're not just working with D-glyceraldehyde this entire time. So we'll go ahead and say that we've got an OH, NH2, maybe we'll put we'll put Br here and H in this case. All right, so first let's go ahead and determine the configuration on this. We've got some crazy stuff attached to this molecule, but Br is definitely the highest priority in this case because it's the largest atom. And then the next thing would be the OH because that's the next largest. And here we've got the NH2 is third and the hydrogen down here is fourth priority. And so we can go ahead and write this, draw the rotation that we need to go from 1 to 2 to 3. In this case, we're moving from Br over here to OH to NH2. And we can see that this is clockwise. And because the low priority group is sticking back into the page, right? It's not pulled up out of the plane of the page because it's not on the horizontal arms, it's on the vertical arms. That tells us that this is indeed R. Clockwise tells us R when low priority into page, meaning vertical. And it means S when low priority is out of page, and that means horizontal axis. Now, if we want to convert this molecule, or if we want to tell whether, let's say, whether this molecule is an enantiomer versus the exact same molecule with this other one over here, what we can do is go ahead and just tell how we got from one of them over to the other one. So in this case, what we've done is hold the OH static, hold the OH steady, and we've taken all three groups and rotated them around. So we moved the NH2 from the far right down to the bottom. We moved the H from the bottom down to the far left, and we moved the Br from the far left to the far right. So we just rotated all of these around, but held the OH the same. This is kind of the same thing as just looking at the molecule from the other side. And so what we'll recognize is if we go ahead and assign all these priorities again. So again, we've got, that's 2. Bromine is 1. NH2 is priority number 3. And the hydrogen is number 4. And we try to draw our rotation that we need around this thing. Now we can see that we're rotating counterclockwise to get from 1 to 2, right? So we rotated counterclockwise. However, in this case, we can notice that the hydrogen is now sticking up out of the page. And so because we rotated counterclockwise, but the hydrogen was out of the page, then we can go ahead and say that this is also an R configuration, just like the other one. And so these two are the same molecule. And again, that's because we held one of them in the same spot and then moved all three of the others. Now, if we were to instead have held 2 of them in the same spot and just traded any 2 other ones, for instance, if we say, let's go ahead and say OH stays where it was, NH2 stays where it is down here, and then we're going to go ahead and put the H on this side and the Br over here. What we'll see in this case is that we will, after assigning all of our priorities, we will have needed to change the direction that we're rotating. So we will have gone from rotating counterclockwise to now clockwise. And H in this scenario is still sticking up out of the page. And so therefore we know that this needs to be S. And so if you change 3 groups around, then that's totally fine. You'll end up with the exact same molecule. But if you only swap 2 of them, if you take the one on the left and swap it over to the right, or if you take the one on the right and swap it down to the bottom, or any combination of just a 2-group swap with 2 remaining the same, then you will have switched the configuration of that carbon over to the opposite. So in the case of this molecule, since we only have one chiral center, we changed the molecule into an enantiomer of itself. I hope that this was able to shed some light on Fischer projections and how to convert between them and how to make sense of them for some of you. I'm going to upload the notes for this in the comments section on this video. Please feel free to comment if you have any questions. I'll do my best to monitor this periodically and see if I can answer any questions. If there are some prevailing questions that a lot of people end up having, I'll go ahead and make another video addressing those. Best of luck studying for the MCAT. Oh, and go to onesourcemedicine.com if you're interested in working with us some more or sampling any of our other resources. Thank you so much. Have a good one.